Danes, can you see my screen?
Yes.
Okay. So basically, when we do the first course, it is free for everyone. But now we put a little bit of fee, which is 200,000. It is around 12 euro, Pekka. 12 euro for everyone, whoever the money will be returned later. So it's kind of a commitment fee. Whoever, surprisingly, we still get a lot of participants, so applicants. So this is the difference with the first course that we did a year ago. So there is a fee here, but for students who active, who come at least 70% attendance, the money will be returned. So I will do a little bit technicality about this course. So what will you learn? You will learn a lot, guys, in here. You will get some basic about thermodynamics that used in metallurgical process. And after that, you will learn how to produce metal and also battery. In here, we will learn how to produce metal like a copper, tin, nickel, zinc, rare earth, and also technology, how to produce the metal using microbe. We will also learn technology to recycle metal and also battery and also some of the kind of mineral processing, but it is used for recycling. So this is the topic that we will get during the course. And for all students, okay, if you want to get a grade and certificate, because later on you can transfer this credit to your own university. Actually, in Indonesia, it is credit. Maybe in Finland, it is equivalent with 5 credit, because you can see it is very intensive courses. 1 month, every day, 2 hours, and there is assignment. So for 2 credit in ITB, it is maybe equivalent with 5 credit in ALTO. So also for Indonesian student, if you want to get some credit, you have to attend at least 70%. So we will give you a kind of attendance form to be fulfilled by you. Also, we record here, so we know how often you come to the course. And after that, besides you have to attend 70%, you have to submit your assignment. The assignment must be submitted to ITB system. So later, maybe tomorrow or next week, I will tell you how to submit the assignment in ITB system. So you will later, the participant, also the lecturer like Pekka, will have access to ITB learning system. It's called EduNext system. In EduNext system, you will download the materials from each lecture. You can obtain the links of the video for every session, because the today lecture, for example, is recorded. So you will see the recording later, and the link will be submitted also in the EduNext, the ITB learning system. And also you have to submit in there also. So when will you get the login? We will tell you later. Not today, but everything will be done in the system. Okay. But for maybe for today material, we will send you by email. But later on, we will send you the login details, and you can access by yourself at any time to the material, to the video, and etc. So what is the because we will give you a grade, you have to make an essay at least 2,000 words. It is about recent development or technological review for metal production, and the deadline is 30 September 2022. So 2 months from now. Okay. So what is the example of the assignment? This is the example of the assignment. The form, don't worry, we will send it later. So this is the kind of the example. It's not too hard. However, we have tour in here. So everyone who do plagiarism from the internet or even from previous assignment, because maybe some student of Indonesia, okay, they try to look for the from previous student assignment and then they copy it without do a kind of paraphrasm or something like that. The machine will detect you that you are doing plagiarism. So please be careful about this and remember you have to submit the assignment. Otherwise, for ITB student, your grade automatically become 0. And it will be shown in your transcript. So remember, don't forget to submit your assignment. And this is still the example of the assignment, the technology, and this is about leaching in Indonesia. But you can select any technology you want, pyrometallurgy, recycling. It is very wide topic. So that's from me. Is there any questions? Any question?
Excuse me, Mas Imam, I want to ask a question.
Yes.
Hello, is
Please.
my voice clear?
Yes.
Okay, thank you very much. My name is Raden Muhammad Nabil Salman Hakim from Bandung Institute of Technology. I want to ask a question about the final assignment. Can we immediately try to work on that from now on? So at the deadline, we will have no big task, something like that. Thank you, Mas Imam.
Of course, it depends on you. We don't see when you start, you work it. We only see you are submit online and the content. We don't care about when you submit it is 1 hour before you work on it, start from today, or maybe you already have some materials. It doesn't matter. Okay. So we don't care about that. We care about quality and times. Okay. Any more questions?
Excuse me, Mas Imam. I want to ask.
Yes.
Let me introduce myself. My name is Muhammad Aan from Institute Teknologi Bandung, and I want to ask about the format. Is there any format for this essay or something like that?
Yes, I already saw you in the picture. There's a format, so we will send you later the material of today from email, so you can start from now if you want to start to write and you have some idea. Is that clear?
Oh, okay, thanks, Mas Imam.
Any more questions? Okay, please remember you have to submit your assignment. Okay. Thank you for Nabil and Aan. Is there any question? Any more, guys? Okay, if not, we welcome first guest lecturer is from Finland. His name is Professor Pekka Taskinen. He is one of the most outstanding researcher in the world. If you googling, if you see Stanford top scientists in the world, they publish some names, and in their list there is 2 names that involved in this lecture. First is Professor Pekka Taskinen, and also later on we will have Dr. Taufik Hidayat. Professor Pekka Taskinen is also my professor, my previous professor here, and professor also of Longgong. So it is nice to have you here, Pekka. to share your knowledge again to all students here from different university, from different country, and time now is yours, Pekka.
Thank you, Imam. So, ladies and gentlemen, today I will talk about, let's see, about sustainability. And his first lecture will deal with common issues, general issues in sustainability, so that can you see my slides now?
It is said Pekka pause screen share. Pekka, it is said that you pause
Yes.
the screen share.
Yes, I try to activate it again.
Okay. Yes.
Yes. Now it comes. So my today's lecture is about general issues in sustainability and things related to metals production. So the production chain of metals is very long, and that is why you need to know the complexity and issues behind metals production in order to understand in which sense metals may be sustainable and what we must do in order to make metals in a sustainable way. This is a simple and very much simplified diagram of metals production, showing various parts and steps in metal production in general. It doesn't relate to any particular metal or group of metals. This is general diagram showing how metals are produced and how they are recirculated, remanufactured, repaired for use, and this is the overall pattern we face in metallurgy when we are dealing with sustainability, and I will show you now few boundary conditions, which are general boundary conditions for all metals, which you need to understand in order to figure out what sustainability means in metal making. So as we know, metals production is based on natural ores and concentrates made out of them, and those ores have been generated over tens and hundreds of millions of years in geological processes, and their amounts are finite. It is true that you don't find ores from every corner of the world. They are in specific places where geological processes have been generating them, and some metals are more common and some are rare. So this is one boundary condition. And the other one very important feature in general in metals making is that most, if not all, smelting and refining processes, whatever they are in pyrometallurgy or hydrometallurgy, so need energy, and that energy is typically today generated from non-renewable sources. So from coal, which is typical source of energy, still years to come. So these are the strict and hard laws of metal making, and because the sources of metals in Earth are finite, so metal making can never be sustainable in very kind of wide sense. So we always face the problem of scarcity of raw materials, scarcity of energy, and there are a lot of things we need to do in order to secure raw materials to next generations, to coming generations, and secure the availability of metals which are needed in the society or societies. So if you look at the world on a very long perspective, so not only years but tens and hundreds of years perspective, so there are at least 3 megatrends which have had very strong impacts on the demand of metals. The first is the growing population, which will be discussed a bit later. The second one is the increasing growth of gross national product. Those two issues are increasing the demand of metals. And then third very general trend is something I call miniaturization. It is a trend which is rather hard to identify in very short term, in months or years perspectives. But if we look at issues which have happened over the last decades, we see that miniaturization typically can be seen there that our cell phones 30 years ago or a bit more were not something you had in your pocket. They were portable but not pocket size, and their capabilities were very elementary compared to what we have now in our cell phones. So this is a good example of miniaturization. So all the devices are becoming smaller and smaller. They need less and less metals, and thus their kind of burden to the societies and to our world is less and less by a unit, but because of increasing population, so those units are growing much more. So this miniaturization can also be seen in issues like photography. Some 30 years ago, your photography was by using film, which is a resource. It uses silver for generating the picture. Nowadays, it's full electronic. It doesn't need any silver for making the picture. So this is leaner and leaner in terms of metals consumption. Also, many things earlier made mechanically are nowadays made by ICT. So computer-based tools, which are not needing so much resources as before. So what has happened over 2,000 years in terms of metals consumption is that in addition to the amount of metals needed and metals demand in general every year, so it has been grown. Also, the number of metals used in the societies have been increased a lot. So if we look at world some 300 years ago, so then we had only few metals in our use. We had used copper and iron, zinc, tin, and lead for almost 2,000 years. But nowadays, so that is 6 basic elements of, or that is carbon is one there, but 5 basic elements of metals. And nowadays, today, year 2000, we have more than 30 elements in use, and this will be the future in metals making. So more and more elements are needed for satisfying the demands of our technological inventions, and this is almost also characteristic to the current societies and the development of technology, that also more elements are needed for running our societies. So this is general picture and pattern of metals world, so to say, and it is closely linked with energy. So that if we look at statistics where energy is utilized in the world, so we see that majority of energy is in fact used in mining industries. So it is the first part of metal making, and as I said earlier, the smelting and refining, making the pure metal, which is not actually consumer product yet. That takes much less than mining and quarrying. So we have also other mines than just metal mines, and that means that these mineral mines are included here, and they are equally energy intensive operations as metal mines. So for this reason, the current trend in our industry, in mining and quarrying, is to convert these operations into electric vehicles and other conveying systems instead of diesel and in some cases carbon-based electricity. So some mining companies are even today capable of showing openly that their mining operation is fully electrified, and that electricity is coming from renewable sources. So this big portion of electricity is turning gradually into green, and thus the use of non-renewable hydrocarbons and carbon-based fuels is gradually decreasing. This is a very local case, but some mining companies located in countries where you have a lot of hydroelectric power, they have used this and show operations with very low carbon footprint. Some 15 years ago, European Union presented one concept for ensuring that our future societies have, among others, metals for their daily lives. And this concept is called circular economy, and its counterpart is linear economy. And European Union authorities claimed at that time that a lot of resources are wasted in old-fashioned linear economy, where we take non-renewable resources, process them, and produce things from them and use them. And in this present type of linear economy, we may be recycling less than 10% on the average in European societies back to the loop, and then most resources are either purely wasted or dispersed into the Earth's crust. So landfill or kind of put aside in some way which does not enable their use in the society anymore. So it is clear in this analysis that these finite resources are wasted in the linear economy, and it doesn't support the present type of standard of living for the future generations, because many metals are used for good in some tens of years. I will return in this lecture later on. So what we must do is this much higher resource efficiency in our processes and systems and in the societies. This is not a problem of metal making, but much more wide problem for the society, for the societies and on the level of societies. So we need in many cases we need to change our mindsets to support circular economy, and it requires major changes in our societies and thinking how people kind of respect these finite resources of our planet. So what circular economy actually is? It is not basically recycling. It is basically extending the life of our resources. So when we have the primary resource extraction, whatever that is, it is farming or forestry or our mining operations. So this is the starting point of resources, and after that we have to think or rethink our industries and our societies in such a way that these primary raw materials are not landfilled as waste in the end of their lives. So there are several loops in the circular economy, several loops for things. So we can use our products again. We can reuse them in some other applications, some other markets, some other uses. We can even remanufacture the product to another application, totally other application, so that the content of resources is remaining in the product, and it gets a new life with some upgrades. And the last and really the last circle of materials is the recycling. And it is the step where we expect recoveries less than 100%. So in each recycle loop or cycle, we will lose metals, we will lose energy. Actually, the use of energy is emphasized in recycling, and that is why recycling will be increasing our use of energy in metal making. So by doing this and acting in societies in this way, so it has been estimated that circular economy will reduce the need of primary raw materials by quarter or even by third, so 25 to 30%. And in metals production and in non-minerals, non-metal minerals use, the reduction is clear but not as big, so 5 to 10%. So compared to the linear economy, so we will see how these estimates will realize in the future, but the concept is there, and our duty is to do our best to make this recycling business and issue to flourish. So we have a lot of features in the circular economy which are not technological as such, not belonging to the art of metallurgy. So the issue, big issue in here is the collection of materials in recycling. So in order to get material in this recycling loop, we need to collect them. We need to find out suitable and effective ways in societies how to collect and also to reuse end of life goods, and that must be in each country defined in legislation. It may be different legislation in different countries, but it must be regulated by governments in order to be effective. On a kind of, to my mind, on a free way, without any legal frame in the legislation, this collection of end-of-life goods will not be possible. It is seen clearly in European contexts where different schemes for making things are established. And one very good example is the beverage bottles and cans, which in some countries are not regulated at all. So you buy a can of soda and you do whatever you fancy with the can after you have consumed the drink. And that causes a lot of aluminium and glass to be wasted in city dams and other landfilling systems in societies. In my country, in Finland, we have used probably 30-40 years a legal system which is putting a small deposit on the beverages sold in grocery stores and other places. It's 10 cents or 15 cents per can, and there is a private company, so to say, who takes care of these bottle and can recycling, glass recycling depots in malls and superstores or wherever you go for shopping, and you get the deposit back when you return your beverage can. And that has caused nice kind of rate of circulation for the beverage cans and PET bottles and glass bottles in excess of 95% in this country. So it is a centralized system which is based on legislation, and it's a private system. It's not government funded or run or anything like that, and it circulates pretty nicely all these aluminium cans, PET bottles, and wine bottle, glassy wine bottles, and everything. So there are several ways of doing this, but the aim should and must be that these cans and bottles are not flowing into dumps, nor they are incinerated for energy, because that is not effective use of plastics either. So we need very good logistics for collecting things, and most evidently we need country level legal actions, legislation for making it true. We have also in Europe already since about 20 years directives which restrict the use of some metals or elements in equipments, typically the use of lead tin alloys in soldering in consumer electronics has been banned since 2006, and this has made the recycling and use of end-of-life electric equipment more safe and more uniform in whole Europe. The other directive is the design for recycling, which is much younger than this lead-free soldiers directive, and the concept of design for recycling enables easier dismantling and recycling of man-made objects in general, so that for example, multi-metal composite things like all microelectronics should be and will be designed and manufactured in a way that it enables easier recycling for those goods, and we will see what happens with many microelectronics devices when this directive comes reality in few years' time. So the whole circular economy as such is rather simple if you describe it in a common language. So the principle aims at keeping products, components, and materials at their highest utility and value at all times. So we shouldn't buy things for one or two uses only. We should keep them alive longer times. So the preferred order of handling of any man-made good or object is shown in this kind of triangle where the most favored option is on top. So prevention of generating waste and going downwards. So energy recovery is on the second lowest level of the pyramid, and disposal. So landfilling typically is the lowest level. In my tomorrow's lecture, I will discuss in more details about the situation in circular economy and sustainability in metal making, but I have here some general issues for you to remember on demand of metals. So the general dilemma in metals is that demand of metals is growing all the time. This graphics shows the situation over about 20-25 years. where we had in 1990s we had excess production, large stocks of metals stored in metals exchanges in the world, and the development of metals price was rather unfavorable. There were low prices, even decreasing prices, and it can be seen here in the iron ore pricing over the 90s and early 2000, and after that the iron ore demand has been growing constantly, not from year to another, but on a average curve. So the same with copper, steel, and also to some degree with aluminium. So those that abnormal period of time was very hard for metal making companies, for mining companies, and it was normalized the situation when the demand of metals was gradually increasing at normal kind of pace, but once those stocks were consumed, and it took not 10 years but more than 5 years altogether. So the demand of metals is growing. This is one fact. And one could still ask in such a situation that why don't we circulate, recycle more? Well, one fact is that the logistics for recycling is not yet here. So many countries, including very industrialized countries, have difficulties, and they are not having well-tuned logistics for collecting metals and other raw materials. That is fact. Not even in Europe we have lots of development to see in the near future. The other thing is that many metals are used in the infrastructure. So we are building apartments, we are building roads and bridges, we are building grids for electricity distribution, we are making locomotives for trains and rail cars. A lot of metal is kind of hidden in those man-made objects, in ships, in railroads, in airplanes, in cars. Well, cars typically have a lifetime of 10 years or something like that, but locomotives are typically in use more than 50 years. roads are built for more than 100 years, and ships are also very, very long-lasting devices in the use. So a lot of metal produced in the past, say 50 years ago, a lot of copper is still in our infrastructure, and it is not available for recycling. It's not available for scrapping. So this means that even if we would like to recycle more metal, it is in our societies, in our infrastructures to serve us, and it cannot be recycled. So this is the fact which we must remember always, that some metals have very short lifetime in the man-made goods, like cell phones. Some people tend to buy a new cell phone, let's say every year or every second year, and basically that old cell phone can be recycled after such a period of use, and the metals contained there are quickly in the use again. But then we have these old metals which are construction metals which are made for electric or heat conduction, like copper, and these are not circulating with such rates that they could be available within years. They are typically available in tens of years, and probably in many tens of years only. So if you look at copper production some 50 years ago, it was about 5 million tons a year here, and if most of that it was used for electricity grids and electric motors, heat exchangers in industry and elsewhere. So it is still in use, and everything, all copper made after 1970 is still in use. So basically we have only this 5 million tons for recycling, when this current level production, the mining production of last year was about 20 million tons. So we don't have more than 20%, 25% copper available for recycling, and that is about the amount we actually had last year. So the second boundary condition is the population, and when we look at forecasts how world population will develop in the years to come, we can see that the present 8 billion plus people here, so will grow still many decades. So it means that even the most how to say estimates showing the quickest decline in the population of world. They estimate that 30 years from now we would peak the population, but after that it should be going down. This is from United Nations estimates, but several other estimates will indicate the growth up to 50 years, 60 years from now, and even some of them don't indicate any maximum population at all, but the slowing down increase only until 2100. So that these curves mean increased consumption of metals, increased demand of copper and nickel and whatever we are producing, and the maximum in here is probably 9 billion in the as the lowest estimate for the population growth, and the other estimates are showing populations of more than 10 billion people, which means 25% more than today. So these features clearly indicate that there will be no end, no slowing down, no decrease in the demand of metals, which in a way is good for us because we are making metals, but there is a clear concern about the availability of metals in the world. This is a simple estimation when looking at metals demand, but there is also another side of the coin, which is typically making the development of metals demand stronger than the forecast of population in the world only, and it is the increasing wealth of societies. So increasing gross national product of a nation, meaning increasing standard of living, means that families and people are consuming more metals. So this will be increasing the demand compared to the population growth only. So, as I said earlier, we have traditional conventional metals like copper, iron, lead, nickel, perhaps tin also, which are needed on a long term with an increasing rate of some 2 to 5%. This is long term, very, very long term increase in many metals: aluminium, copper, zinc, iron, and we believe that this growth will continue. But there are metals which may have large variations from this standard kind of well-behaving demand pattern of conventional metals, and some call those metals as technology metals, but like gallium, indium, tellurium, germanium, among others. But there is also new metals like stainless steel, which is not an element but alloy, which was invented a bit less than 100 years ago. Its growth has been about 10% over the last decades, and that growth rate means that we will face shortage of several metals within our lifetime, and that means that there will be preferences in the metal making industry. Substitutions will appear in the industry. So substitution of typically alloys which are made nowadays with some new alloys which are not containing metals which may be critical, and their availability is low. Typically stainless steels, which consume most of nickel produced today. So some 65-70% of nickel produced is used for stainless steel making. So the strong electrification of the societies need these metals which are well electrically conducting and which can be used for storage of energy, and those batteries contain today, probably not 10 years from now, but today they contain nickel, they contain cobalt, which are so small metals that if the electric cars are becoming as popular as forecast in many papers, so there will be no nickel available for stainless steel very soon. So these estimates here are from Australian IMM bulletin, which has actually taken into account this electrification and use of and the need of nickel batteries in electric cars. So this big step between 2020 and 2035, much bigger than in other metals. It is due to estimated demand of electric cars. So we will have turbulent times in terms of demand of metals, and that means that a lot of, say, scientific work is needed for finding out the suitable substitutes for those metals which are becoming scarce in terms of their reserves and resources in the world, and this is one driver of our profession. So material science people will be and have been focusing already some time what to do with these metals which are becoming critical in terms of their availability. But forecasting is rather difficult, and this kind of forecasts which are currently made for estimating the needs of for example battery metals, they indicate so rapid and so huge growths in the demand of certain metals that they must be taken very, very seriously. So how to on a very long term, how to estimate the demand of metals is in many cases using the concept of intensity of use. It is the intensity of use is the consumption of certain material divided in a country, divided by the population, and when that ratio is plotted as a function of gross national product, so you will see curves like this. This is USA, Japan, which in early stages of industrialization and low gross national product levels showed very steep increase in intensity of use of steel, and then it has been flattened out, even going down, and the same here with China and Canada, also Europe has behaved in a way that it follows. So at a certain point of gross national product, the societies have been built their infrastructures, and the consumption of for example in here steel has been reached the level of maintaining a stable society, not building new roads, no new harbors, no new ships, but just to replace the old ones, and this is a concept which has been used by UN and other kind of independent evaluators, but there is some kind of uncertainties in these curves, and they typically are related to exchange rates of currencies. So sometimes currencies may have been fluctuating very much, and this is making the comparison of periods and countries difficult, because there may be levels of changes in the gross national product of 10, even 20% from one year to another, even if no national changes have happened, but only the value of their currency of that country compared to this is they use here the international dollar value, so whatever that is, so it may have caused this kind of hiccups here over the long periods of time. So this is how and in which way we can try to estimate long-term trends in metals consumption, but it has been recently pointed out in the literature that there are kind of basic problems like this exchange rate, which may be very exact comparisons, scientific approaches in here difficult. So let's look at this energy issue here, because our business will still be based on new mines, new ores found, because we need due to the growth of population and due to the growth of gross national product, we need increasing amounts of metals. So question is how that metal will be processed in the extraction stages, including the mining. And the carbon dioxide footprint is essential when we try to struggle keeping the global warming within 1.5 degree. So, as I said earlier, there are mining companies who already have done this. They have changed from fossil fuels to renewables, and that means that their carbon dioxide footprint is less, but this is not yet possible to all parts of the globe or all countries, and a lot of things must be improved and changed before we can say that metals production is sustainable, and it is following the common agreements made in, for example, in the Paris agreement for CO2 emissions. So we will face the increase of energy price. And here is, this guy is from Iceland, I think. Recent evaluation of energy price over this 200-year period. So 100 years ago it was very low. Now we are probably 10 times higher than in 1920s, and we will go at least 4 to 6 times higher energy prices in the future. So that means that we will have high energy cost in extraction of ferromanganese, ferrochromium, and ferronickel, and that means that we are putting more and more money into stainless steels. These are not chromium nickel stainless steels, what these guys here analyze. They are replacing nickel with manganese, which is available instead of using nickel, and the price of this kind of alloy is expected to rise hugely. Not yet, not today, but it will be 2-3 times higher some 50 years from now. But after that, when nickel has been exhausted in our reserves, so we will see a huge increase in the alloy price. So this is a forecast which includes, in addition to the increasing price levels of energy, but also decreasing resources of nickel, and combine those into price estimates on a very long term. So this is not commonly used period of time where these estimates are made. Typically they are 50 years or something, but this is much longer in terms of for stainless steel and its substitute compositions compared to our present production. The other thing is the availability of metal as a total. So if we look at the demand patterns in near future for the electrification or required by the transfer from petrol driven cars into electric cars, which is expected to happen in Europe within 10 years or 15. So we can see that these small metals, nickel, cobalt, lithium, which are used in energy storage technology, so batteries, they are developing fast, but very soon the demand of cobalt, for example, so it is exceeding what we have in the known reserves and resources of cobalt in the world. So we can see here that this average demand, and it's only up to 2030. It is exceeding already within 5 years the production. So average supply from mine and recycling sources, and in the end of this decade, we are seeing significant deficiency in terms of cobalt, and this means that we don't have the same batteries in our cars or other devices some 8 years from now than we have today. So there must be much different recipes for the battery energy storage materials than we have today, and they cannot be based on cobalt. So next metal we are suffering severely in the same ways is nickel, and lithium comes a bit later. Okay, this is my lecture of today. So now I could answer to your questions if there are any.
Okay, Pekka. Now the time is question and answer, guys. So you can ask any questions related with the Pekka lecture today. So please raise your hand and mention your name, and please deliver the questions to Pekka. Basically, any question, Pekka, right? Okay.
Any question, any topic?
Yes. Please.
Be brave.
Yeah, be brave. Don't be shy. Okay, Farhan.
Hello.
Yes.
We can see and hear you.
Okay, before I ask my question, I would like to say thank you for Mr. Professor Pekka Taskinen and Masima for this lecture. First, let me introduce myself. My name is Farhan Armunanto, and I'm from Faculty of Engineering, majoring in Metallurgical and Materials Engineering, University of Indonesia. One of your lecture slides said that circular economy does not belong to the art of metallurgy at all. And my question is, why the circular economy does not belong to the art of metallurgy at all? It said from one of your slides, in your lecturing slide, it requires many boundary conditions. And what are those conditions and why? Thank you, Professor Pekka Taskinen, for your lecturing. You gave us detailed information about the trend, data, and demand about metal production. Thank you.
Yes,
okay, Pekka.
probably
Also, there's
sorry.
actually another question, Pekka. Maybe, I don't know. It is from Alex. He asks about, is that energy price actually adjusted with inflation or price as when it is recorded? In the chat. Also for everyone, don't forget to fill the attendance. The link is in the chat also.
Yeah, I think the energy prices in that paper, they were the current currencies, and not taking any kind of inflation in account. But yeah, if that issue is interesting to the person who asked this, so I could probably send him her the paper, which may give a better idea of the investigation. But Farhan, to your question, I'm afraid I expressed myself a bit too simply way, in a bit too simply way. So I meant that circular economy is not only metallurgy. It has most of things it is including is out of metallurgy. So we need these logistic issues and how people think about returning their waste, so to say, used beverage bottles and used cell phones back to the circulation. So they are not metallurgical issues. They are more issues for the society and for the governments to educate people to think in a right way. So at least I have a couple of old cell phones in my home, which I should have been thrown to recycling already years ago, but still they are in my cabinets here at home. So this is the mindset issue. So the inhabitants of a city, they must understand, or a country, they must understand that this returning of beverage cans and glass bottles and plastic bottles, it is essential, and it is your personal duty to do it, and it is not any academic issue as such, but nor an issue of metal making. And that is what my meaning was to say, that it is not entirely metallurgy. It is a lot of other things included in there. Did I make myself clear now? Farhan?
Is it answer your question, Farhan? Oh yeah, it is understood.
You are muted.
Oh yes, he replay in the text. Okay, guys. Any more questions? Maybe two questions. Don't be shy, be brave. You can raise your hand, so I will let you after that. Question? We still have 5 minutes. Don't be shy. Okay, if there is no question, then thank you very much, Pekka. We will see you again tomorrow.
Thank you. Till tomorrow.
See you tomorrow,
Bye-bye.
guys. Bye-bye. Don't forget to fill the attendance, and we will
Thank you.
email you
Bye-bye.
about the material today or later in EduNext. Bye-bye.